Hello, students. Today we want to talk about some families of functions that we can incorporate into a piecewise function, and also families of functions that we can transform with function transformations. So these are topics that are indeed universal. That is, you can use these ideas now and for the remainder of your STEM mathematics and use them to great effect. So one good thing about college algebra is that it provides us with some very excellent techniques that assist us in the calculus sequence and beyond. So let's get started with some of the more familiar functions that we deal with on a regular basis. So let me share the screen. Now, what I've done here is just summarize a few of the functions that we will use often. Now, when you get to calculus, you may look at some functions. One of them that tends to be very popular with discontinuities is the greatest integer function. And we may have occasion to say something about that. But right now, we want to start with the more fundamental functions that we can use to great advantage. Now, what I've done here is just put down the basic ones. We see that we have the standard quadratic, which is f of x equal x squared. Again, we're looking at the largest possible domain, which is all reals, and the range, of course, would just be 0 to infinity. Again, we're squaring a real number, so we can never have a negative result. Now, of course, you can think about applying transformations where you reflect this graph in the y-axis, which again wouldn't do anything because we see it's an even function, or at least it appears to be. A reflection in the x-axis, we can stretch it vertically, we can do all kinds of things. So we can end up taking this function and manipulating it to produce other interesting functions that are related to what we call the parent. So sometimes when you talk about families of functions, you think about the standard functions, which we call the parent functions. Okay, another very popular function is the cubic function. Again, f of x equal x cubed. Again, this is a very good example of an odd function, just like we saw f of x equal x squared is an excellent example of an even function. Again, y-axis symmetry, origin symmetry. But here we see the domain. The largest possible domain is all reals, and the range, of course, covers all reals. And noted here is an increasing function. We don't have the value of having the derivative in the prerequisite courses to the calculus sequence. So a lot of our increasing, decreasing arguments will have to be based upon functions that we're aware of and our intuition and just the computation of points. But we will do our best, and we will often use functions that we know to be increasing when we are doing our calculations, and that's certainly fine. The next function that is very popular and very useful in mathematics is the square root function. We can write it with the radical or the 1/2 power. Again, this is very popular when we're doing inequalities. The domain, of course, would be all non-negative real numbers, and the range is just the same. And it has the characteristic shape. It's increasing, but as we say, it takes its time to increase. Now, another popular function that we've already seen and spent quite a bit of time is the absolute value function. We have the conjunction theorem, the disjunction theorem, all kinds of interesting properties of the absolute value that we have used in our work. Very important in the calculus sequence. And of course, the definition is a piecewise definition. That is, by definition, the absolute value of x is just x when x is non-negative. And of course, it's the additive inverse of x when x is less than 0. So you get the standard y equal x and y equal negative x, that characteristic V shape of the function. Again, we see number 6 is just the standard y equal x. So here we just simply truncated this, and then we replace it with y equal negative x. So this would be a good way to figure out why this particular function looks this way. And of course, if we just reflected this particular function in the x-axis, we would get y equal negative x, which would explain this piece here. So the negative is just a reflection in the y-axis. We'll talk about that with the function transformations. And then another popular function, kind of a relative to the square root function, is the cube root function. And of course, we can take cube roots of any real number. It's certainly real to take the cube root of a negative number, so we do not have to restrict the domain here. The domain is all reals, and of course the range is all reals. But like the square root function, this function is increasing, but it certainly takes its time to do so. So again, the idea is that we have an increasing function, and then as we take the calculus and we have the use of the derivative, we will be able to describe these functions in a more precise way. But for now, we are certainly happy with what we have here. So the family of functions will be functions that we will manipulate and utilize the theorems and the strategies to create new functions that can be very useful to us in mathematics, and of course in science and engineering and other STEM disciplines. Okay, so what we want to do is now check out some of the function transformations that we will use on the families of functions. Now, what I've done here is I've summarized these so we can use these as we do examples. Now, what I've written here is function transformations, and under this I have put universal. These work for any function. We know the function is the most useful abstraction in mathematics, and any of these transformations are valid, any function you use. So if you're in physics, if you're in chemistry, biology, any STEM field, even in business and accounting where transformations are used, these will all work. Now, some of the more complicated ones are the horizontals because they're less intuitive. The verticals tend to be very intuitive, and the axial shifts or axial reflections tend to be maybe in the middle, but not as abstract as the first two here. So the horizontal shifts, what we're going to do is we're going to fix an h, so some positive number like 2. And we want to shift the graph of the function to the right by h. We will replace x with x minus h. And this has to do with the fact that this is a horizontal transformation. And so students must get used to the fact that a shift to the right will mean a replacement of the independent variable to x minus h. And again, the idea here is that when you are doing a shift, you are now associating the particular value at x minus h with the new value at x, and that's why the graph gets shifted. And I'll say more about that. Again, this is less intuitive, but it will certainly make more sense as you apply it. Now, the shift to the left can be done by replacing x with x plus h. Again, we think of the transformation of replacing x with x plus h, and then we're associating the value that's to the right with x. And so as we shift it back, we see that we actually get the shift to the left by h, again, with the x plus h replacing x. So when you think about what's going on algebraically, it makes sense, but the initial visual is a little counterintuitive. Now, to compress a particular function horizontally, or when we think about compress or we think of stretching, we have to use another counterintuitive procedure, and I'll say more about this. If we fix a c between 0 and 1, then we can actually stretch the actual graph horizontally by a factor of the reciprocal. So for instance, if we replace x with 1/2 x, we can stretch horizontally by a factor of 2. So that's why we reciprocate here. And now if we want to actually compress the graph horizontally, we will fix a number c bigger than 1 and replace by x by cx. So for instance, if c is equal to 3 and we replace x with 3x, then we have compressed the graph by a factor of 3. We've made it 3 times smaller in the horizontal distance. Okay, so this is very important here. Again, we think of the horizontal compression and stretch like the horizontal shifts as being counterintuitive replacements, but algebraically, they make perfect sense. Again, these are the two that you will have to spend the most time on just to make sure that you've got the concept down correctly. Now, let me go to the axial reflections, which are kind of in the middle. If we want to accommodate an x-axis reflection, we simply apply the additive inverse to the function. That will basically reflect the point in the what? X-axis. So that's easy to affect. That is, we are affecting the function value, f of x, by adding the additive inverse. If we want to reflect in the y-axis, then we want to replace x with its additive inverse. So this will associate, again, the value of f of x with the negative x. So this is a reflection in the y-axis. And y-even functions don't appear to show any difference because they are already symmetric relative to the y-axis. So interchanging points would not have any effect on the quality of the graph. Now, the easiest ones are the verticals. So if we want to do vertical shifts, we can fix a k positive. And so if we want to shift upward by k, we simply add k to the value of f. Very intuitive. And if we want to shift downward by k, we simply subtract k from f. Remember, in the horizontal and vertical shifts, the fixed numbers are positive so that we can write these correctly. So that's always very important. Now for the compression and stretch, very intuitive. If we want to stretch the y coordinates, we simply multiply f by a number bigger than 1. So we fix c to be bigger than 1, and we have a stretch by c. Very intuitive. Now, if we want to compress, we were thinking maybe we want to make the y coordinates 2 times smaller, so we can actually multiply the coordinate f of x by 1/2. So again, this is a compression by 1 over c, which is the same way we wrote the stretch here in the horizontal situation. So again, the vertical transformations are very straightforward because we are applying the transformation to the y coordinate to the function. So that's very straightforward. When we are actually changing the independent variable in the horizontal situations, that's when we have to be more refined in our algebra, and the actual transformation is less intuitive. But we will find these to be extremely, extremely helpful when you get to the pre-calculus and you study trigonometric graphs using these transformations. So again, very, very useful, very, very effective in mathematics, STEM in general. So when I say universal, these work for any function. So we will use these in some examples. And again, it's nice to have a list of these so you can actually study these and have them with you as you do your homework. I think you'll find them very useful. Now, I want to look at just a few examples of some functions defined in pieces, and then we're going to start manipulating them. So let's look at some functions defined in pieces. So we'll just say f of x has the following definition. And we'll use some of our families of functions. So we'll say that f of x equals x plus 4 when x is greater than or equal to 2. And then we'll say that, if you will, f of x will be the square root of the absolute value of x when x is less than 2. Okay, so that's kind of an interesting function. So again, we have the definition x equal 2 or greater to be x plus 4. And then for x less than 2, the definition is the square root of the absolute value of x. Now, the way I've set this up, this is a very interesting function because we can see that it will be defined here. I didn't write this down just so it would be undefined. That would be a waste of time. So let's just check a few values. Let's do f of 10. So f of 10 would correspond to the first row because, again, 10 is greater than or equal to 2. So we would use the first definition. So this will be replacing x with 10. We get 10 plus 4, which is 14. Let's try another one. Let's say we do f of negative 5. Well, now what we can see, negative 5 is less than 2, so we use the second row. So we will replace x with negative 5. So we have the square root of the absolute value of negative 5. Well, the absolute value of negative 5 is positive 5 by definition. So just remember, I'll just do a little sidebar here. The absolute value of 5 is the additive inverse of negative 5, which is 5. So we end up with the square root of 5. So what's nice about this particular definition is that it gives us a function that may be useful to a problem that we are working. So let's note the following. So note the domain of f is defined for all real numbers. We have not left out any numbers in the real line, so we have negative infinity to infinity. Now, another interesting thing is if we think about this, we have x equal 2, so the minimum here will be 6 and greater. So we know that we have 6 and any number bigger than 6 here. So that's what the first line gives us. Now here, we notice the same thing. So we have, let's just notice some values here. We go to 0, so we have the square root of 0, but any other number that we actually work with will give us a number bigger than 0. So that will cover all of the positive numbers. So now we can see the range will actually be more so dictated by this. The range of f will be all positive numbers, including 0. So note on the first line, we get 6 and greater, but the second line covers more in a more expansive way. That is, we have the square root of the absolute value of 0, which is 0. So we see the smallest the principal square root can be is actually 0, but then all the numbers after that other than 0 provide outputs that are positive. So this will cover all positive real numbers, including 0. So that's a very interesting function that I made up there. But again, remember the piecewise function is whatever you want it to be. It's not something that you actually do just for an academic purpose. If it turns out that this helps you to solve a problem, then that's very good. Now, let's look at some other examples. What I want to do is check out some of the transformations. So first, let's look at one of our parent functions. I like to start out with like maybe a quadratic function and then apply some of the transformations, and then maybe start out with a function equation and unravel it and figure out what the graph is. So here's the first one. We're going to start with x squared. So x squared will be our parent function here. So this is our f of x equal x squared. That's our parent function. And what we want to do is apply the following. That is x-axis reflection. That'll be the first transformation that we apply. 2, right shift by 3. And then the last one we can do vertical compression by 2. So that means we're going to have to multiply by 1/2. We want to vertically compress by 2. So we're going to make things twice as small. So we'll do a little arrows to indicate the transformation. So we'll say x-axis reflection. So again, that would mean multiplying the function by the additive inverse, or multiplying by -1, attaching the additive inverse. So this will reflect the graph in the x-axis. Right shift by 3. Notice this is horizontal, but the right shift by 3 characterizes the horizontal shift nicely by 3. So we replace x with x minus 3. So we have negative x minus 3 quantity squared. This started to look like, the standard quadratic function. And then vertical compression by 2. So vertical compression by 2. So we multiply by 1/2. So we have the 1/2 times the negative, and then x minus 3 quantity squared. So this is a way to actually take a given parent function and apply the transformations in a sequential process. And applying these sequentially gives us this. Now let's go ahead and work on a graph of this. With the parent functions, we can actually graph because we know what the parent looks like. So let's do that. And we'll move some simple points. When you're trying to get a simple graph, you can just think of the very simple points that are on the parent. So let's just recall that we have the following points. That is, we have 0, 0. We have 1, 1, and we have -1, 1. Those are 3 simple points on the parent graph, and we can figure out what happens to these points by these transformations. So x-axis reflection just means that we replace all of the y-coordinates with their negatives. So we have 0, 0. So I'll just follow these. We have 1, -1. And then we have -1, -1. Then we have a right shift by 3. So remember, when we do the actual function transformation, we replace x with x minus 3, but to actually manipulate the coordinate pair, we add the 3, which we do geometrically. So all of the x coordinates are changed by the addition of 3. So we get 3, 0. We get 4, -1. And then we get 2, -1. And then the last one is vertical compression by 2. So all of the y-coordinates get multiplied by 1/2 to compress by a factor of 2. So we have 3, 0. We have 4, -1/2. And we get 2, -1/2. So what's interesting about this particular example is that we can get the shape of the new function using the shape of the old function. So let's go ahead and graph this. We'll spread it out a little bit. So we have 3, 0, 1. We'll spread it out so we can see it. And then we have 4, -1/2. So I'll spread this out a little bit. So -1/2, about right here. And then we have 2, -1/2. So we can connect again what's going on with the original function. So we see we can actually extend this if we want. So if you like, we can just kind of start extending this because we know what the parent function looks like, something like this. So when we started out, we were right here. We're right here. And so then what we're seeing, if we just go back to what we've done here, I'll move this up. We have the x-axis reflection, which reflects the graph in the x-axis. We shift to the right by 3, and then we compress. So when we compress vertically, the function actually becomes wider. It's less elongated. So this basically identifies with what we've done to the particular parent function. And notice these points give us the new coordinates for the transformed graph. So what we want to be able to do is also, for instance, we have to think about what the functional equation is for the transformation. And then as we manipulate the points, that's much more intuitive. When we do a right shift with an ordered pair, we simply add that amount to the x-axis or to the x coordinate. But we're saying functionally, we have to do the transformation, which is the x minus the h. So the functional equation and the geometric strategy do differ. The geometric parts are often very intuitive, but the functional equation is more complicated in the horizontal sense. So that's a good example. Just remember, the way to get the simple points is to start with easy points on the parent graph and then transform them. And then what you can do, if you like, you can extend this. So this function, we want to just go ahead and write it. The new function we can just call g of x equals negative 1/2 x minus 3 quantity squared. So that's the new transformed quadratic function here as we see in the red. Okay, let's try another one. The function transformations, like I said before, are extremely powerful, and they give us wonderful techniques to work with functions in general. So let's look at the following. Here's an example from your lecture notes. That is, we have the following. And I'll just make one up. This particular one is actually pretty simple. And let's see, let's see here. Yeah, that's so simple. Let me make one up. So here we go. Say we have the x-intercepts of f of x, this function, are, and just say we have two. Let's say we have -3 and 2. Compute the x-intercepts of, let's just say, f of x plus 2. Okay, so now what does this mean? This corresponds to a left shift by 2, left shift. So that means that the x-intercepts must be shifted to the left. So we have to subtract 2. Remember, this is the shift to the left by h, and h in this case is 2 because we've added the 2. We've added the h. So the new intercepts so we'll subtract 2. We have -3 minus 2 equals -5. That's a new intercept. And then we have 2 minus 2, which equals 0. Those are new intercepts. So if you want to do this based on what we did last time, we could just say we have the point -3, 0, and we have the point 2, 0, and we have, in this case, left shift left shift by 2. My techniques for this are very easy because you described in a very simple way the transformation. So we subtract 2 because we're doing a left shift. So we get -5, 0 and 0, 0. So you can affect it using the technique from the last, or just make this convenient assessment, thinking about the geometry of the actual transformation, and then you get this very easily. So just remember, the transformations are very, very convenient and very powerful, because we may not, you think about what the transformations do, and you think about shifting graphs, up, down, right, left, stretching, compressing vertically and horizontally, and then thinking about the axial shifts. Now, the only other thing that will be possible to us will be rotation, but that will only be something credible when we have the trigonometric functions, because that will require that rotation about a point requires trigonometric functions. So let's just see here that even a problem that's very simple like this is difficult unless we have the use of the transformations. So let's try some more. So let's just start with a function, ladies and gentlemen, where we're asked to graph it, but we want to unravel it to make it into a simple function. And see, we start with the simple function and create the new function like we did before, but now we're doing the backwards problem. We're not starting with the parent. We get the more complicated function, and then we want to unravel it. So here's an example. I'll say use transformations. Use transformations to graph the function. And the square root functions tend to be some of the most useful ones. So let's do this. So we have h of x equals, let's say we have a -2, and then we have the square root of, let's see what we can do here. I'll keep the numbers good for us. So let's say we have 6 minus 3x. So that'll be enough transformations for us. We won't shift it upward or downward now, which we easily could do, but let's go ahead and focus on this. Now, we see that the parent function would be the square root function, and if we actually analyze these correctly, we should be able to get a transformation from the parent square root to the more complicated h of x. So first we need to rewrite this so we can identify some of these transformations. And I've got 2 axial reflections here. So we have -2, and I'll do the square root for now. Let's go ahead and factor the -3, and that'll give us an x minus a 2 to the 1/2. So notice what I've done here. I want to make this look like the transformations, the functional transformations. So factor the -3 from the -3x to give us -3 times x. And of course, the 6 is retained by multiplying -3 by -2, absorbing the negatives to give us 6. So now this is starting to look a lot better. So we've got several transformations going on here, so I didn't need to add any more. So notice here, the first thing we want to do is we've got this negative here, so that would be a y-axis reflection, and then we have the 3, which would be a compression by a factor of 3, because 3 is bigger than 1, and then it looks like we have a shift to the right by 2, and then as we move out, we have a vertical stretch by 2, and then an x-axis reflection. So let's summarize all of those. So what we want to do is build the new function using the transformations in a sequence that provides this function. Okay, so let's start with the square root. So we can start with the y-axis reflection, y-axis reflection, which will give us the square root of negative x. And now we can do the compression by 3 times smaller, compression by 3. So replace x with 3x. Okay, so that gives us exactly what we need. Now to get the x minus 2, we'll just do a right shift by 2. Right shift by 2. So this gives us the square root, negative 3, x minus 2. Right shift by 2. Now when we look at this, we're almost home free. We just have to move outside. And so we've got a V stretch by 2 and then an x-axis reflection. So those can be done in any order. So we have V stretch for vertical, V stretch by 2. So that gives us 2 square root negative 3 times x minus 2. And then the last one will just be x-axis reflection because we have a negative. The sequence must allow you to transform the parent into the more complicated function. And as long as you accomplish that, your sequence is fine. If your sequence has bad order, then you won't get this function. And then you've created another function, which is not this one. So notice it takes 1, 2, 3, 4, 5 transformations to go from the square root to the h of x. Okay, so now let's just go ahead and move some simple points. So let's do 0, 0 because we don't want to work too hard. And we'll do, let's see what, 1, 1. And let's do 4, 2. Because these are easy functions to square root, or easy numbers to square root. So we do y-axis reflection. So again, we replace the x's with their negatives. So 0, 0, negative 1, 1, negative 4, 2. Okay, that accomplished this. Now compress by 3. Now notice this is a horizontal, so I need to say H compression. I should have put the H there because you need to know, like we have the V stretch, H compression by 3. So we have to divide all of the X coordinates by 3. So we get 0, 0, negative 1/3, 1, and then negative 4/3, 2. Again, universal and uniform. Okay, so now right shift by 2. So if you like with these thirds, just think of, and here again, I say it, but I don't write it. So let me go ahead and put the 2 there. That's one thing about the shifting. If you don't write it, you can see what you missed out as you start moving the points. Now, if you like, just think of the 2 as just a denominator of 3. So this will just be 6/3. Okay, so think of it like that. So now what we're doing is we're adding 6/3 to the x coordinate. So go ahead and get the common denominator so it's easy to do. Of course, we don't need that for this. We'll just put a 2 there. So we have 2, 0. And then the 6 plus the negative 1 will give us a 5/3. And then, of course, the 6 plus the negative 4 gives us a 2, so we have a 2/3. Okay? So it's all self-correcting. Everything is there. Just make sure your order's good, and you can always verify that as you go through each of the steps. Now we've got the right shift that we've done. Now we knew a V stretch by 2. So multiply all of the y coordinates by 2. So we have 2, 0. We have 5/3, 2, and we have 2/3, 4. Let's keep going. The last one is the x-axis reflection. So we just add or multiply all of the y coordinates by -1, or they all get an additive inverse. So we get 2, 0, 5/3, -2, and 2/3 -4. And this gives us the new function right here. So I will say this. This procedure allows you to use the shape of the parent function to draw the new function. And so what we see is that the point that defines the minimum of the square root function basically just gets mapped into 2, 0. Not a lot happens to that because it's on the axis. It's at the origin. And so when we do the y-axis reflection, nothing happens to it. Now, when we do the h compression by 3, nothing happens to it, the x coordinate. There's no change. But with the right shift by 2, we get a change. Okay, so we expect that, but notice the v stretch by 2 is not going to change it, and then the x-axis reflection is not going to change it. So only one of these transformations actually impacted the 0, 0. Okay, so that's what's very nice about these transformations. They affect the process seamlessly. It's like it's magic. You don't really have to do much except apply the transformations in a good order, and then you're done. And now we can sketch the new function. So let's go ahead and do it. I mean, we've got, you know, downstairs a little bit. So I'll go ahead and draw this so we can get our new picture. So I'll stretch it out a little bit. So we have 2 zeros, so 1, 2, and we have 5/3. So 5/3 is just what 1 2/3. So it's kind of bunched up. So let me do this. Let me stretch it out just a little bit more. So we have a little bit of space here. So everything's just not smushed together. So we'll do like a 1 and a 2, and we'll make this axis a little bit smaller. So we have 2, 0, and then we have 1 2/3 -2. So let's see, 1, 2, 3, 4. So a little smaller scale here. So 1 2/3 right here, -2, about right here. So 1 2/3, about right there. And then we have 2/3, which about right here, -4. And so we can draw our graph. There we go, right there. And of course, it'll keep going. We can extend it. Again, this is not a work of art, but we know what the graph looks like, and we know what the new points are. So this is our h of x. So now when you look at this, if you replace the x with 2, you just get the square root of 0, which is again 0. And then, of course, if you do the 5/3, the 3's absorb, and you get 6 minus 5, which is 1, and -2 times square root of 1 is -2. If you put in the 2/3 here, the 3's absorb, and you get 6 minus 2, which is square root of 4. That gives you 2. 2 times the -2 is -4. So these should work out in the original, but what is nice about this particular transformation is that you also see what's happening to the x coordinates that you would not see otherwise. So the beauty of this is that with the transformations, we can move the simple points in a way to get this beautiful graph here that calculus wouldn't help us do. This is where students must be made aware of the fact that there are certain techniques that transcend more complicated techniques. This is such a masterful way to graph this function using the transformations, and it gives you exactly what you need. It transforms the parent function points to the new graph here, and we have this beautiful graph that again is exactly what we need. Now notice what's interesting here. You might look at this and think, well, you know, when we get a 0 here, we've got just the square root of 6. And the square root of 6, that's between 2 and 3, and you multiply by -2. So we're at least the graph is fairly good here, maybe a little bit lower, but our graph is not so horrible that our scale is just done us in. So the idea here is that the transformation process can be a much better tool of determining a function graph, and also the fate of certain points here. Now, of course, the idea here is that you can always, like I said, you can always figure out what you get for the y coordinate just by substituting the points, right? But you don't get the x coordinates that way. I mean, you could always run it backwards, but the idea is that what we're trying to do is get a picture of the new graph. So not only do we need the y coordinate, we need the x coordinate. So that's what makes this process really, really very nice. Okay, so use this example as a way to organize how you sequence the actual transformations in a way that takes you from the parent to the actual function h of x. Use this as an example because it covers all of the ideas that you will need to be able to do. The functional equation manifested in the geometric procedure. Geometric procedures are often very intuitive. The functional equations aren't. And so you have to be able to identify them in a way that allows you to manipulate the coordinates correctly. Okay, let's try some more. These are actually kind of fun, aren't they? So let's see here. Where's that other example that I want to do? Okay, we got that. Let's see if I've got another example here that might be of use to us. Graph functions, we've got reflections and all that. So let's try another one that again, where we actually take the function and unravel it. That's, I think, where you get the most use out of this. So let's look at this. So we have the following. So I'll say graph the function using transformations. Let's try another one like the one we just did. Graph the function using transformations. So let's look at the following. Say we have, let's call this g of x. And let's see here, if we cubic function, we just did the square root. So let's think about maybe something that would be interesting for us. Let's think of the absolute value. And so we'll say the following. So we'll say, let's do another vertical axial transformation. So we'll do like a -3, and we'll do a, let's do a 4 minus a 1/2 x. So we can do a horizontal stretch plus 2. Okay. So again, we've got properties of the absolute value that could really just make this very simple. And so we can use some of them, we can use them, but we want to characterize this in terms of a transformation process. So I may say this: if you use properties of the absolute value, notice with the last problem, we didn't have the luxury of nice properties of absolute value. We can't move numbers around as effectively with the square roots because we just don't have that capability. So we had to work a little harder. Now, here, let's go ahead and transform this into a I guess, into a form that allows us to identify the transformations that we know about. We have 5 of them. So first, what we want to do, we can either factor this or just use the fact that we have the properties of the absolute value. So remember, we can always flip things around with the absolute value. So if we have 4 minus 1/2 x, we could just write that as 1/2 x minus 4 using properties of the absolute value. So let me remind you of that. So we certainly have that available to us. And absolute value is our friend. So the absolute value of a minus b is just the absolute value of b minus a. So we have that luxury that we don't have with the square root function. So feel free to use it. So we have -3 1/2 x minus 4 plus a 2. Okay, so now what we can do, again, since this is simpler, we don't have to work as hard. We can now go ahead and factor the 1/2. So let's do that first. So -3 1/2 x. Okay, now, of course, if we factor the 1/2 here, we've got to multiply that by 2. So that's minus an 8. Okay, so again, factoring the 1/2, we just hit that with a 2 and a 2, 2 over 2, get rid of the 2 downstairs, and the 2 times the -4 is the -8. So of course that's correct, but always check that. And now let's use the fact that the absolute value of a product is the product of absolute value. So if we have AB, that's just the absolute value of A times the absolute value of B. So what I'm trying to do here is use properties of the absolute value with the function transformations. And since we have these beautiful properties, we might as well use them. Now, so this will be -3 times the absolute value of 1/2 times the absolute value of x minus 8 plus a 2. Okay, but now, of course, what's the absolute value of 1/2? It's a positive number, so that's just 1/2. So we get what? -3 times 1/2, so -3 over 2 times the absolute value of x minus 8 plus a 2. Okay, so this has really simplified the function from the beginning. Okay, and now when we look at this we can contend with. Notice the parent function is the absolute value function, and so we could do our right shift by 8. Then we could do what? We could do the vertical stretch by 3/2. We're going to make it bigger. We can do the x-axis reflection, and then we can do an upward V shift by 2. That's it. So there are 4 transformations here. So now we have reduced this to something that we understand. Notice we didn't have to worry about doing any kind of horizontal stretching here because we just use the properties of the absolute value. So that's certainly available to you. So don't use the transformation if you don't have to. If certainly we can make this simpler. So now let's see what we get. So we'll start with the absolute value. And if you like, we'll just do the right shift by 8. I don't remember the 8 this time. Right shift by 8. Right shift by 8. So that gives us x minus 8. Replace x with x minus 8 to shift the graph to the right by 8 units. And now if you like, let's do a V stretch by 3/2. So this gives us 3/2 x minus 8. And now for the negative, let's do an x-axis reflection. So this gives us -3/2. Let's see, -3/2 x minus 8. And then lastly, we just do a upward V shift by 2. So upward V shift. I try to use as few words as possible, but just so we know what's going on, upward V shift by 2. So that's a -3/2 x minus 8 plus a 2. That's it. So we needed 4 here. So we could just, again, be kind of lazy and do the easy points, which again would be 0, 0, 1, 1, and negative 1, 1. So we just think of making the V there, where we have the 0, 0, the 1, 1, and the negative 1, 1, and just move those points. And then if we want to extend the graph, we know what it is because we know the shape. Okay, so just think of this as transformations made easier because we have the properties of the absolute value. And we spent a lot of time with absolute value with the last section on the conjunction theorems, the disjunction, the properties of absolute value. Those are so important to what we do with equation solving and also working with the calculus. So we need to remind ourselves of them. So now let's go ahead and do the right shift by 8. So this will be adding 8 to all the x coordinates, 8, 0, 9, 1, and then of course 7, 1, just adding 8 to negative 1. And then a b stretch by 3 halves. All of the y coordinates get multiplied by 3 halves. So we get 8, 0, 9, 3 halves, 7, 3 halves. And let's do an x-axis reflection. So all of the y coordinates get a negative. So 8, 0, 9, negative 3 halves, 7, negative 3 halves. And then, of course, we want to do an upward V shift by 2. So we can just think of that as 4 over 2 to get common denominators. So basically, we'll just think like we did before, plus 4 over 2, of course, to the y coordinates. So again, we'll just write that one as a 2. No need to write it as 4 over 2. So we have a 2. And then we have 4 plus a negative 3. That's a 1/2. And then we have a 4 plus a negative 3. That's a 1/2. Okay, so this is really simple when we think about doing it this way. This is a really, really remarkable technique. So now we can draw our new graph. It's just moved over, and it's stretched in the horizontal direction. So again, you can do like a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So of course, that's not really necessary, but we'll just go ahead and do this, and we'll stretch out the other axis a little bit. And we'll just do a 1 and a 2 to spread this out a little bit. So we have an 8, 2. And then we have the 9, 1/2. And we have the 7, 1/2. All right, there. Okay. And of course, we can extend this if you like. So this is our graph of g of x. Now, of course, if you wanted to substitute these values into the original, you get the same outputs. So here, if we have the 1/2, in this case, we get the 4. So we get 4 minus 4, that's 0. So we just get plus 2, which is a 2. And if we put in the 9, notice in this case, we have the 9 halves, 8 halves. So that's an absolute value of negative 1/2, which is 1/2. And so we have negative 3 halves plus 2, which is 1/2. Same for the 7. So you can always get the y coordinate by just substituting the numbers, but that doesn't give you where the x's live. So now what we see is that we start out by shifting to the right, then we do a the stretch. So we stretch the graph so it's more narrow. It's not as wide, it's more narrow. And then we do with the reflection. So we do the x-axis reflection, which again flips everything in the x-axis, and then we do an upward v-shift. But notice I've written the v coordinates a little bit larger here, so it looks more pronounced, but we shift the graph up, but it's opening now downward. Okay, but see, this technique gives us such a wealth of information. And so we get a beautiful graph that calculus will not help you do. Okay, so this is what I'm trying to impress upon you. If you think about what we're doing here, ladies and gentlemen, we are simply applying very straightforward function transformations to what looks complicated. But when we apply the transformations, we get a very beautiful graph with little or no work. Of course, we have to do the analysis here, but you can move any point you want that's on the original graph. The nice thing is that we take the complicated graph, we transform it from the parent, and then we can just take simple points on the parent graph and move them to the more complicated points, or not necessarily more complicated, but points that we don't really know. So again, 0, 0 gets mapped into 8, 2, 1, 1 gets mapped into 9, 1/2, and negative 1, 1 gets mapped into 7, 1/2, and we get this nice picture. So what I've tried to show you here is that we can take the functions in pieces, we can create any kind of function we want, have as many pieces as we need. That can be very convenient when you're working with economics or businesses, where you have certain categories. Okay, so you see that in STEM, and you see that in accounting and economics. So functions in pieces can be very useful. And then, of course, we just follow the dictates of the function. We say, well, what value of x do we have, and where does it fit in the formula? So that's very straightforward. We just follow what the formula tells us. Okay, and then just as some repetition here, get my do with my parent. Oh, here we go. And so to do the transformations, what is the best evidence that we can use? What are the best pieces? We can use the parent functions. So when we did the square root function and the absolute value function, we could use all the properties of absolute value here. Here we didn't have as much, so we had to work harder, but still we got a really nice graph for low input. But the main thing, ladies and gentlemen, are the transformations. Okay, so the more complicated part of moving things around is affecting the algebra so that we can see the transformations. You usually can see the parent function right away. Then you take the parent function and you sequence the transformations, just like we did here. You sequence the transformations so that you start here and you end here. So the original function may require some manipulation to get to the point to where you can visually see the transformations. And then you can apply in an order that gives you exactly this. I'm not saying this order is unique, but the order provides the transformation from the parent to the necessary g of x. And that's what your transformation sequence should do. Uniqueness is not important. Correctness is what's important. So as you work on the functions in pieces, follow the dictates of the definition, and then as you apply the transformations, just tell yourself what's going on geometrically, okay, when you're trying to move the points, but then tell yourself what's going on functionally. How does the equation of the function change with the given transformation? And all we have to see is that the what is it, Roman numeral 3, 4, and 5 are relatively straightforward. We just have to be a little bit more vigilant with the horizontals because they are not as intuitive. So once you have this down, once you have these down and you use them and you practice with the sequences here, you will find that you have very, very powerful techniques. And when you get to the exponential and logarithmic functions, and also when you get to the trigonometric functions in pre-calculus, you will find a great use for the function transformations. So I can't emphasize more how important these are. They are fun to use, and you improve on your algebra as you manipulate the particular functions to recognize the transformations. So please spend plenty of time on this because the rewards of this will be great. And you will see this in your science classes. You'll see this in your engineering classes, and it will help your understanding. Okay, that's all I have to say about this, and we'll see you soon. Thank you.